Okay, good morning everyone, and welcome to the 2017 Royal Tyrrell Museum Speaker Series. Today, the Royal Tyrrell Museum and its cooperating society are proud to present a familiar face, Dr. Takuya Konishi. Takuya is an assistant professor in the Department of Biological Sciences at the University of Cincinnati in Ohio. Takuya is originally from Japan. He began his undergraduate studies at the Kochi University, but after his first year, he transferred to the University of Alberta, where he obtained his bachelor's degree in earth sciences and biological sciences. He stayed at the U of A to pursue his PhD in biological sciences, where he studied the systematics of Palaeontology Mosasaurs. After successfully defending his PhD, Takuya came to the Royal Tyrrell Museum as a postdoctoral fellow and stayed here for 3 years. He later moved to Manitoba, where he worked as a professor in the Department of Biological Sciences at Brandon University before being hired 2 years ago by the University of Cincinnati. Takuya's research interests revolve around the evolution of mosasaurs, a group of extinct marine lizards that reached a worldwide distribution during the Cretaceous. As such, Takuya's interests have led him to conduct research all over the world, including in Canada, the US, France, Belgium, England, the Netherlands, and of course Japan. Today, Takuya will describe the peculiar adaptations of a special group of mosasaurs called the Halisaurines. So without further delay, it is my great pleasure to present you Dr. Takuya Konishi.
Can anyone hear me? Good morning, thank you. I could have had another cup of coffee, but I'll just try to stay up throughout my talk, and I hope that makes two of us. Okay, so let's begin. Today's focus. I usually talk about mosasaurs from Alberta, our backyard, or from North America. But today, we go across the water, so to speak, on the other side of the Pacific, and the specimen that you are seeing right now comes from northern Japan, from the island of Hokkaido. And this particular kind of mosasaurs has been quite an enigma for over a century, because we really didn't have good specimens for a long time, let alone to understand what their lifestyle might have been. And it seems that this particular very spectacularly preserved specimen from Japan can answer quite a few of those questions. So without further ado, I'm going to just advance. Okay. So, but before I get into mosasaurs whatsoever, let me, bring you back in time and go back to the Mesozoic era, where the name, the age of reptiles, was coined by Louis Agassiz way back when, and that kind of makes sense given that reptiles really dominated all the major three ecosystems. In the air, you had not only early birds, but also, of course, pterosaurs, some of them becoming so large, 12 meters wingspan. And, of course, on the land, your favorite, must be your favorite, dinosaurs, the non-avian dinosaurs, technically speaking, ornithischian dinosaurs here on the right, to the right, and then saurischian dinosaurs to the left. And last but not least, of course, in the sea, you had this. The sea was teemed throughout the Mesozoic with these various types of reptiles that reinvaded that marine realm after their ancestors evolved on land. And so really spectacular radiation of reptiles, certainly dominant in respective ecosystems. And you have those wonderful fossil records that we enjoy learning from to date. Now, as I already said, however, reptiles, whether you are in the water or land, they ultimately evolved first on land. So that means they were air-breathing animals. They had lungs just like you and me. So just like whales have to surface every now and then to breathe through their blowholes, these reptiles that are found in the sea also were breathing air. And so their adaptation to life in water is secondary. secondary adaptation to life in water. So in other words, they are not breathing water, breathing oxygen through water using their gills. They didn't have the gills like the fishes. Those days are gone, so that's just my cartoonish representation that they are air-breathing animals. Okay, good. So what do I have next? So let me just do a bit more, introducing you, continuing to learn about what was going on in the Phanerozoic, so the 550 million years or so of last 550 million years or so of our history of Earth. So what I have first here is basically a sarcopterygian fish tetrapod transition. Dictatic rosei from Nunavut is a very famous, iconic fishapod that shows both fishy and tetrapod characters, such as neck. Having neck is a tetrapod characters. Your goldfish doesn't, shake its head because it cannot move its head. And the Dictatic could. Now, so that is, beginning of the tetrapod, the vertebrates, conquering the land. And then later on, so that was 380 or so million years ago, 350 million years ago or so, we have this at least first known reptile-like tetrapods. Hylonomus, the first amniotes, of course, and that really signifies further, the acquiring more independence from the body of water. So they could lay eggs on land rather than doing so in the water as in amphibians. Now, however, only 30 million years or so after the evolution of this Hylonomus, someone decided to go back to the water to kind of spoil all their effort. But in any case, so that's Mesosaurus. That's the Permian marine reptiles. Mesosaurs were important for Alfred Wegener when he was proposing, the continental drift and so on, because you could find them on, both sides of the Atlantic Ocean from the Africa and South America and so on. But in any case, Mesosaurs, although they are perhaps shallow water dwellers, they were really, marine adapted aquatic reptiles. Okay, now then going into the Mesozoic, then you have this series of re-invasion by different disparate groups of reptiles. Here is Sauropterygians, Nothosaurs, Plagodons, and so on. Ichthyosaurs, that's a different group altogether. Marine crocs go back. Crocodiles went back to sea during the Jurassic, becoming really fish-like. And then even groups of Sphenodon groups, so those are Tratara that you find in New Zealand today. They go back. And then sea turtles made its way back. So turtles made its way back to the ocean 110 million years ago or so at latest. And then, of course, one of the last lineages of reptiles that went back to the sea are those lizards, and they are the Mosasaurs. They lived from about 100 million years ago all the way to the end of the Cretaceous. Now, many of those went extinct, of course, minus the sea turtles. And then the sea was quite vacant for a while for the vertebrates. And of course, whales then, or mammals, go back to the sea. And by 40 million years ago or so, you see this rather dolphin-looking thing swimming around, and that is the primitive whale. So I hope this kind of shows you how many times, how frequent and a common phenomenon it was that tetrapods just went back to the sea. Now, so just to last punchline here, whatever reptile groups you see today, some of them are just, many of them are not really marine at all, but during the Mesozoic, they had some kind of truly marine taxa represented. You can even add birds, diving birds for the Joe's special group here. And then here's the Elasmosaur, like Plesiosaurs, Ichthyosaurs. These two, as I indicated with the dagger mark here, they are totally extinct. They never left their descendants into the Cenozoic. So here is Mosasaurs, the group that we are going to be talking about today. And so let's enter Mosasaurs. And I have a danger ahead of you. because of this. So I didn't mention specifically where I got it, but in any case, you know where it is from. And I have a couple of statements to make here. It's too big, way too crocodilian, and they call it mosasaurs. So this is certainly a, I guess, the popular culture version of what mosasaurs might have looked like. But to me, it's really too knobby on the back, too toothy. The teeth shouldn't have been so exposed like crocs today. And certainly, it wasn't that big. It was big, but up to about 40 feet in length, 12, 13 meters. OK, now moving along. This is a little, better, actually, much better reconstruction of mosasaurs. You can see how, for example, how scaly this thing is, because as I just said earlier, they are basically lizards with flippers and tail fin. Both of those works were done by Julius Sotonii. Of course, it's a beautiful rendition of, I guess, Bruce Tyrannosaurus pempenensis from modern Manitoba. This is also Bruce, I think. So, any case, so those are what they might have looked like. And as you can see, one thing for sure, they now are reconstructed with this shark-like tail fin, which we believe most of the mosasaurs had. Now, moving along. So, as I said, they are strictly late Cretaceous. They were really late in the arena, going back to the sea. They just didn't do that until the very last part of the Mesozoic. And we now know freshwater as well as marine taxa. Freshwater, at least one species is known from Hungary. That's Palaeontology inexpectatus. And also they are grouped under the particular group of reptiles called Squamates. Squamates include lizards and snakes. And what makes, they are big. Here you go. That's a big thing here. OK, that's our specimen, prognathodon. OK, so what makes mosasaurs squamates? Squamates, for one thing, would lack this particular bone that would have been present in a primitive diapsid reptile's lower temporal bar. You'll find that in dinosaurs too, but that bar is gone. And so it's easy then for us who look at the bone structures to identify whether you're looking at a lizard-like reptile or croc-like reptile or dinosaur-like reptile. So here, mosasaurs, like in this lizard skull, lacks that bar. Lower temporal bar is gone. And that also frees this quadrate bone somewhat so that this joint at the star can be mobile. Now, how mobile that joint was, there's a debate. I don't necessarily buy the argument that that joint was mobile for all the known lizards. And I certainly have some opinion about that, about mosasaurs, but let's just move on. Okay. Squamates, so now sometimes you get really lucky, though. Sometimes you have the matrix surrounding the skeleton of a, say, Tyrannosaurus here from Kansas that preserves the impression of the skins. Nice diamond, very regular diamond-shaped skins, overlapping, and like fish scales. The overlapping scales are the hallmark, another hallmark, soft tissue hallmark of lizards and snakes. So here is a skull of the mosasaur, and you can see on the head, the scales are more hexagonal, and they're not really as overlapping as those body scales. And if you look and compare those two images with this thing, here's a green tree python. The skull has this, rather diamond-shaped, not diamond, but hexagonal-shaped, larger scales that are not really overlapping, just like that. And then here on the body, it's more regular in terms of the shape and the number and the size, and they are overlapping scales. So really, sometimes, this is another confirmation that we are looking at some kind of lizard-like reptiles that went back to the sea. That's mosasaurs. Now, but they really didn't look like most lizards that we perhaps imagine today because of their, adaptation, rapid adaptation to life in water. They wanted to swim fast so that they can catch fish. And I guess I just made a wrong Lamarckian statement just now, and I apologize. But they didn't want to do that, but they were selected for, body plan like that. So whoever got this kind of body plan was more favorably selected because they were capable of pursuing fast-swimming predators. Fish items, for example. So here is a skeleton, about 5.5 meters long. This is from Kansas chalk, much older than our specimens from Bearpaw here, 85 million, 83 million years old. This thing, you can see how downturned the tail end is, and that would have supported this rather shark fin-like tail fin right there. So really, their skeleton really looks more like today's dolphin or killer whales rather than skinny lizards. But in any case, so here you go. But what I'm going to be showing you today is that the mosasaur that perhaps didn't really show that much fishy shape, and rather a bit more lizard-like in a terrestrial lizard-like in that it is skinny and elongate. But in any case, this is the last set of introduction. So how many species we have? 70 species or maybe even more. And under 6 subfamilies. So you have Tethyssaurinae, Agrosaurinae, Talosaurinae, Palaeontology, Halisaurinae, Mosasauridae, which is perhaps the most dominant member of the mosasaurs, followed by Palaeontology Mosasaurs. But what we are learning today is that this so-called fish shape body plan of mosasaurs evolved more than once in this mosasaurs. In other words, mosasaur paddles evolved more than once, multiple times. And we just happen to be calling all of those mosasaurs. But some of them are actually not paddles. They have limbs rather than paddles. And those that are in these red boxes, they are the ones that show this kind of fish-like morphology. And tucked right underneath, right there between these two groups, is the Halisaurine Mosasaurs. And this one is not figured here. And that's for one thing because it was not very well known to make a reconstruction. But also, it wouldn't, even if it was, it wouldn't have looked very much like the other ones. Because this is a skeleton in Uppsala, in Sweden. This was originally from Kansas, but it was purchased by the University of Uppsala, and it's right there. But what you see here is a really, really narrow tunnel-like torso, not so much, streamlined. And if you look at the paddle too, it doesn't really have a typical paddle, well-developed paddle, where these 3 elements should be much shorter, and then you should have more finger bones beyond that point. But really, this is kind of intermediate in terms of the limb and the fin. So it's these ones that we call the Halisaurians. Okay, so that much we knew. This was old specimen. This was collected by Sternberg. So this is old specimen. We knew about this, but not so much more. So today I'm gonna talk to you about something that came from here on the northwest part of the Pacific. This is showing the major localities that yielded mosasaurs in general, not just Halisaurians. But you can see right away there's a big geographic gap in the fossil record of mosasaurs across the Pacific Ocean. It's a lot of known from here. Surrounding the Atlantic basin, but not so much surrounding the Pacific basin. And so little did we expect to find this rather rare group of mosasaurs from Japan, but that's what happened. Okay, so getting into the specific locality and the age of the specimen comes from northern Japan, Hokkaido. The town of Hobetsu is right there, southern Hokkaido. And there's a creek nearby that basically cuts into the marine sediment of the Cretaceous time. And you have nodules every now and then that tumble down to the creek, and that's where you find those specimens. And here is an approximate horizon of this specimen here, and this is near the lower part of the lowermost part of Maastrichtian. So about 70 million years ago or so. Here's a creek. This is actually where the specimen comes from, but this picture was taken some years afterwards. Very nice place. here is a Hakobuchi formation. And this is a typical nodule that could contain, some kind of vertebrate material, or maybe ammonite. And here's a creek called Pankirosanosawa Creek. So here is a find of the nodule with the bones showing here. And this was found on August 9th during the summertime. And Hokkaido being northern part of Japan, it is quite nice and cool. But summertime being summertime, they still have those nice herpetological fauna. So in this particular case, it's a rather dangerous pit viper that was trying to get into the field vehicle. And I guess this was a kind of a lucky charm in a way, because this was some kind of lizard afterwards. So, okay. Now, this particular site and the horizon has also yielded different mosasaurs before. And this is the paddle of this, the other mosasaur type that's been known, that is Mosasaurus hobbesiensis. You can see this paddle is very, very developed paddle. Very short humerus, tibia, radius and ulna, and you have really, big surface, broad surface of the paddle. So that shows a greater degree of secondary aquatic adaptation, more fish-shaped, more piscine-formed mosasaur was right there in the same place and time, basically with this, the new material that we found. Okay, so now, however, and I guess I was sent this photo of the specimen just coming out of the nodule sometime towards the end of 2009. And so when I was here, I received the photo images showing, what do you think this is? And initially I said, oh, this looks like a Palaeontology mosasaur, which was known from Hokkaido area before. And of course, I was not thinking anything about halosaurines. But it took 2 years, more or less, from the date they started preparing until the finish line. So the reason for that is because it is found in the concretion, and the concretion being so hard, but the bones are really delicate, they decided to do the acid preparation using formic acid. So what they did was that they first coat bones, exposed bones, with paraloid, and then leave the concretion with a paraloid coating on into the 5% formic acid overnight. Soak the concretion next morning in water for 10 hours to get rid of that acid, then dry it. Repeat 1, 2, 3. Average progress, 1 millimeter per treatment. So 2 years. Now, here is the August 15th, 2010. Here's a nice parietal showing here at bone at the top of the head of the lizard. And at this point, I wasn't still sure what to call it. I could have called it Palaeontology, but then it gets more. And by this time, I see something more that really doesn't make it Palaeontology at all. And it was quite obvious, like the daylight, that this was that Halisaurine Mosasaur, but only that it is from Japan. So you get more and more in both sides. The bones are still glued together with the matrix, last remaining matrix. Very delicate. But in the end, they came apart from each other very nicely, and we were able then to make the cast out of individual elements. Had it been totally articulated specimen, this wouldn't have been possible. Now, good news is that it wasn't so hard for us to, classify it under a certain subfamily of mosasaurs. For one thing, it's got this nice triangular boss at the very posterior end of the frontal, and that is a hallmark structure of it being a Halisaurine Mosasaurs. Really narrow frontal. This is a forehead bone. Here's the orbital margin. And so now, here showing all the previous localities that yielded specimens of Halisaurine Mosasaurs, and you can see this white star now added to, from the Hokkaido, Japan, really filled this great geographic gap that existed basically across the entire Pacific. So this really tells us already, just purely based on the fossil record, that Halisaurines were cosmopolitan, at least in the northern hemisphere. There's no question about that. And if you look at their ages, they are Campanian and Maastrichtian, i.e., they are later part of the Cretaceous, later part of the late Cretaceous, not the early part. So they were doing very well for whatever reason, alongside with these huge, giant, fish-shaped cousins. And that was very, and plus they were found in the same deposit. They were not, it didn't seem like they were living closer to the coastline, shallower water, but rather they were found in the same shale bed. So what's going on? But let's have a look at the specimen itself a little bit closely so that you see it is beautifully three-dimensionally preserved. It is three-dimensional. This is a brain case. Nothing seems to be distorted. It's just a brain case right there, just 70 million years old. Minimally or not at all deformed. For example, this is ectopterygoid, rather small bone, really thin. This is the right one. And what you see is that it not only preserves both sides, you can have this nice, gentle, subtle curvature preserved on this really tiny, small, thin element. That really tells you how little deformation is going on. And so that was quite surprising. And of course, if you look at places like the internal surface of this particular bone right in front of the eye socket, you see just minute details right there. It's very thin ridges, the articular surface, everything just is there. And of course, it has a lot to do with that painstaking, very patient preparation that was performed at the Hobbes Museum for 2 years. So lots of credit has to go there. So all in all, the skull of this specimen can be reconstructed fairly accurately and will provide insights into A, specific bone by bone, and B, overall cranial anatomy of this mosasaur, which is great, exciting news because, as I said before, this particular group of mosasaurs has been kind of enigma for over a century. So this part is the part that you have to really work hard to stay awake. Specific comparative anatomy, you get a bit of a kind of a real-world paleontology experience. I know I have a broad audience group, but anyway, this is what first part here basically is trying to understand to determine if this thing is new to science. In other words, is it a new species? Is it a new genus? Who is this? And to do so, you have to, of course, make an apple-to-apple comparison. But the difficulty here was that other apples are kind of half, complete, or even less than that. So, but I did what I could do, and I think we have something to say about this thing. And then later on, I'm going to come back to the overall anatomy of the skull anatomy of the mosasaur. So please bear with me. All right, so first one, we're going to compare this specimen against this thing called Halisaurus arambogi. Arambogi is from Morocco and recently published in 2000s. And you have a couple of things here, but I'm going to just show you the actual figure here. So here's the frontal of the Halisaurus arambogi. This is frontal of our specimen. On the ventral, this is dorsal view. This is ventral view. One thing that you notice here is that the frontal really has these ridges here. You can see running ridges. Those ridges are diverging towards the snout end of the animal on the Halisaurus arambogi. That's not the case with this one. That ridges are actually more horizontal. And you can see how narrow this area of this specimen is compared to that. And so that is basically what I'm trying to show here. It doesn't perhaps make much sense to you, but this is a ventral view of this kind of frontal. And you see this angle here going kind of this way. That would be in contrast with this rather parasagittal orientation of that ridge on this frontal of our new specimen. You can also see that here, comparing the parietal bones, the part of the brain case, this foramen here on the Halisaurus arambogi has this rather raised rim that is not present here. And also this lateral process, post-orbital process, I believe, of the parietal here is rather expanded distally on our new specimen, but it is going tapering right away. So there are those tiny differences. And finally, two more things to see. This is a quadrate bone that was mobile in squamates in general. So if you look at this space right there, it's broader, it's narrower, more like a slit here. And if you look at the lower jaw towards the coronoid process where the jaw closing musculature insert, this superior border of this back half of the jaw is elevating towards the coronoid bone. But that is quite flat, leveled in the Halosaurus arambogi. So in any case, it's a different thing from Halosaurus arambogi. Next thing is Platyspondylus. This comes from eastern coast of North America. I think described initially by Marsh. And this is the oldest, this is the oldest known species of halosaurians. So just looking, this is our specimen, dark one. This is the Halosaurus Platyspondylus. You have a little bit of plateau or shelf here that is not very present here. And if you look at this area, this is the back end of the jaw. You can see it's nice round suture here between syringular and the articular, and the angled here rather between the syringular and the articular. This is a Hokkaido specimen. Okay, so it's different enough. Okay. Next thing is called Phosphorosaurus oriliebi. This Phosphorosaurus oriliebi was described by Dolo in the 19th century based on the specimen that was recovered in Belgium. And this is perhaps one of the most enigmatic and strange-looking members of Halisaurine Mosasaurs. And people just really had a difficult time, to know where to place this, even amongst the Halosaurians. But in any case, it's got a suite of strange characters, which I'm going to explore for now. For example, compared to this specimen, you see how the parietal has its big opening here. Parietal foramen is actually invading the back end of this bone, the frontal bone. And it seems to have really narrow frontal here. And it's on top of that, it has what I would interpret as some pathological deformation right posterior to the parietal foramen, which of course makes it look very strange and different from all the rest of the Halosaurians. But of course, this is the only specimen known to this species. So anything this particular individual holotype shows, is potentially unique to that taxon, which is something that we have to always keep in mind, not to think other possibilities, the variation and so on, outside of this particular individual. But in any case, the one thing that is interesting about this particular Belgian specimen is that this is its quadrate. And you see now this space is rather reminiscent of this narrow slit-like gap that the Japanese mosasaur specimen shows. So that's something that caught my attention when I was in Belgium looking at their holotype. Now, however, earlier workers, 2012, they have made some notable observations based on this holotype, Phosphorosaurus oriliebi. This is a holotype in Belgium. And it seems that they took what they saw at face value, so to speak, without no thinking or without critically evaluating the potential deformation, postmortem loss, etc. So what they said, I can focus on the 1 and 2. So one thing that they said was this parietal bone. And the parietal bone has two components here in the anterior region, parietal table, this center portion, and this sticking out portion that is post-orbital process. Now, they thought that the frontal, at the back end of this frontal, the frontal was so narrow that this entire frontal parietal suture was formed between the frontal and the anterior border of the parietal table alone, but without this particular process. And yeah, it looks like this frontal bone at the end, is symmetrical. It seems it's complete right there. But it's very odd not to have anything going this way to go for the frontal not to reach this edge of the parietal. So I was really, speculative about their assertion. And they also said, back part of the skull really are, dorsoventrally flattened. and that's not very, that's contrasting, that's different from other specimens of halosaurines. So I kind of looked around, and here what you see right there, that bone is called postorbitofrontal. And it has this negative impression here that would receive both this end of the parietal and that end of the frontal. So if you look at that bone here, this is the right one, what you see, if the frontal indeed was narrow at the very back, I would expect this basin to be shaped more like that. This is where that process of the parietal would fit. But this area shouldn't be there because the frontal would have ended before that space. But that's not the case. That means this area, actually, there is a frontal. In other words, frontal just missing these posterolateral ends of the bone taphonomically. And in fact, you do this, very similar. If you took that postmortem distortion loss into account, this Phosphorosaurus oriliebi frontal really is quite similar in our Hokkaido specimen. So, in addition to the quadrate, space similarity, this kind of was leading me to kind of think that, maybe Hokkaido specimen is more closely related to these things. Now, looking at the back part of the parietal and the brain case, yes, everything seems really squished and compressed, but that's not really anatomical feature. It's rather a geological feature, if you will. Just compare this specimen from Hokkaido, which is exceptionally three-dimensional, to this Belgian specimen. There is no way that this was the real thickness of the parietal, and that influenced the entire brain case too. So of course you would have rather narrow antroventral process off of the supratemporal, for example. You don't have to understand any part of that sentence. But that's just basically a taphonomic artifact. So with that, basically, what we saw was that this Belgian specimen, our species, is no different, not so that different at the end, in the end, from any other known halosaurines that we thought are quite distinct from Belgian specimen. So, any case, diagnostic characters should be visible characters minus taphonomic alteration. It's our job then to decipher which ones are taphonomic and which ones are not. So, okay. So the last thing is this specimen that I already showed the skeleton of in Uppsala in Sweden. And this is from Kansas chalk, Santonian in age, one of the oldest ones that we know of. And this is a skull. You can see the margin of the orbit is rather converging anteriorly rather than being concave. And also anterior to this orbit, you have continuous, you have also converging borders in front of the orbit, but that's not the case with this one. This one has more parallel-sided borders. But all in all, after doing this and doing a bit more of analysis and rechecking the characters and things are apple-to-apple comparison, etc., this is what we ended up getting. So all the halosaurines are here. Here's the outgroup. This is a new phylogeny per our work. And our specimen, which is not only new, but also we were comfortable enough to place it under the same genus that Belgian specimen belongs to. So this now is known as Phosphorosaurus ponpetelegans. Ponpetelegans, elegans meaning elegant, elegant preservation of the specimen. Pompet in Ainu language, native language of Hokkaido, Ainu language, pompet means stream. And so elegant stream is the specific epithet for this specimen, for species. Okay, so great. Now that's good. That's usually where my paper stops. So what that means is that when you're having insomnia, you really should grab one of my papers. But here, luckily, this was what I had. So we did all the work, that decided what this species is. It's new, great, good news. But we were left with this thing. So we made a cast just so that we have backup, for the whole type. But it was so tempting to do a bit of, Lego work. So then I asked Mr. Alan Lindo at the U of A to do a bit of reconstruction. And So that's where the second part of my talk is leading to. Here it is. It's beautiful, but puzzling. And it's beautiful. I mean, it's just so symmetrical. And those are not 3D printed, so to speak, to make the reverse image, but rather they are all based on the real specimens that came out of that nodule. And we could get this much complete. And just, I mean, if it was like made of modern day bones, I would be very, convinced that this was something that was living just yesterday. But in any case, just beautiful thing. But one thing that particularly strange about this specimen, unlike any other known mosasaur bone, like a skull architecture, not only the orbit or the eye socket was big, but also, as you can see here, this is a front view of the specimen. The eye was so well exposed in this aspect. That's so very strange. And I'll just let you explain why that's the case. Anyway, the cast was made in Japan, assembly in Canada. Sounds like some kind of IKEA product. Okay, so without being too playful. So here is a typical mosasaur skull, nicely preserved in 3 dimensions. This is Mosasaurus missouriensis from I believe, from Wyoming, or maybe South Dakota. But any case, here you can see this is the orbit. This is eye socket. And from here all the way to the tip of the snout, you can draw these 2 nice triangular, converging line, nice and triangular. And if you look at the top of the skull stays beyond or above the level of the eye socket, as you can see here. And eyes right there, that's the level. And if you look at a typical mosasaur from the front end, you cannot really see any orbits. You can't see them. And that makes perfect sense because, going back one slide, if you have something, eyes that are visible right here, that means that post-orbital portion of the skull was flared out, and that would have produced all sorts of turbulence. And that's not really a good design for you to be a good swimmer, isn't it? I don't think so. You want to reduce the drag while you're swimming predator. But so this was quite contrasting what we find. So here I'm expressing using this Tyrannosaurus skull at the Field Museum in Chicago with our specimen. Those cross X's show the same landmarks, and this is just my PowerPoint, doing. So it's not a morphometric analysis or anything. But you can see how yellow and blue crosses are showing. Yellow is post-orbital. Blue cross is pre-orbital landmark and marker. And you can see yellow is quite further out on our specimen. Yellow is basically in line with the blue in the typical mosasaur skull. And that displacement, if you will, of the yellow cross is as a result of this rather long, laterally projecting stalk-like jugal process of the POF, post-orbital bone. And that allows it to, have the eyes facing almost forward. Now, it didn't stop there. If you look at the red cross here, okay, so that is the side of the maxilla, the upper jaw bone. And it's quite high up here compared to the orbit area here in the Tyrannosaurus, but it's rather low here. So if you look at this, this is, first of all, that's just showing the post-orbital and pre-orbital landmarkers. But then, if you look at this, so that red cross right there, that is showing the top of the maxilla here. And that top of the maxilla here, of course, in typical mosasaur is in alignment with the top of the orbit. But that's not the case here. It is quite lower than the top of the orbit. And here, around here, the snout got really so low, like your shoe, compared to this profile. So all that in combined, what we found out based on this reconstructed skull was that it's got a broad post-orbital region behind the eyes. It's got a narrow rostrum in front of the eyes, and also it's got low depressed rostrum. Now, 2 and 3, according to Stevens 2006, reduce interference by the rostrum on your binocular vision. So we take binocular vision for granted. We use both right and left eyes to see things in front of us, and that way we can perceive the depth. But if I happen to have some kind of book right along my nose, and that makes this division between my left field of vision and right field of vision, although I might be looking at the face of, say, Francois right now, my depth perception is not functioning because there is a septum that prevents the overlapping of the two fields of view. So having a tall snout in front of the eyes, like Mosasaurus or Tyrannosaurus, exactly is prohibiting or blocking that effective establishment of the binocular vision. That is not the case with our Hokkaido specimen, is it? So then we got into this analyzing or surveying the range of the binocular field of vision in various lizards. And what you find is that the binocular field of view, which is the angle of the overlap between the two fields of vision, in living lizards are rather narrow, 10 to 20 degrees typically, with the maximum known in this desert monitor, which is 32 degrees. Now, vertebrates with these field of overlap greater than 20 degrees can drive some kind of distance perception. So you don't have to have 45 degrees, 35 degrees. You could have 20 degrees, and you could have this perception. But obviously, greater the overlap, the more more accurate your depth perception becomes. So in reptiles, it so happens, including birds, this binocular field of vision is substantially greater in those that use binocular vision in predation than in those that merely detect prey on the basis of their motion. In other words, the latter is an example of sit and wait and ambush. That is, that those ones happen to have less overlap between the two fields of view. So here, the tree-dwelling snake here, it's got really high BFOV. Obviously, peregrine falcons or the major birds of prey typically show this rather forward-facing eyes, and you can kind of compare that with, say, pigeon, which has eyes, or ducks that has eyes on the side. Now, if you look at the snakes, because we are talking about lizards, the Cretaceous Mosasaurs, the VFOV is consistently greater in nocturnal taxa than in daylight taxa, which was independent of their habitats, whether it was, whether you are comparing the terrestrial snake, clubroid snakes, or arboreal clubroid snakes, the ones that had greater BFOV happened to be the more nocturnal adapted species. So those are kind of the data we could get from the extant examples. So now I started comparing the apple to other apples. So between this Hokkaido specimen with, say, Mosasaurs and other ones that had a nice three-dimensional preservation of the skull. So here, first one, this is Mosasaurus missouriensis. This is Phosphorosaurus ponpetelegans. Next one is Plotosaurus benisoni against Phosphorosaurus ponpetelegans. This Plotosaurus is known to be really, really advanced in terms of their postcranial anatomy. It really had a deep body, very, very hydrodynamic, and hypothesized to be a long, sustained swimming marine reptiles, almost like an ichthyosaur, like Mosasaurs. Okay, in any case, we measured this BFOV for those specimens, and surprisingly, Plotosaurus, although their body is really, really piscine or fish-shaped, their overlap was really only 22 degrees. So they are not really using their eyes to pursue the prey in terms of gauging the distance. 28.5 degrees for Mosasaurus missouriensis, and then 35 degrees conservatively for the Phosphorosaurus ponpetelegans. So the combination of those two anatomical traits, then, the wide postorbital cranium and narrow and low snout, is key to establishing a well-developed binocular vision, as it was shown in P. ponpetelegans Among mosasaurs, though, P. ponpetelegans exhibited indeed the greatest gap overlap in this particular trait by at least 5 degrees. Certainly, it was bigger than the desert monitor, 32 degrees, I believe. So again, this has a big range of overlap. And there's a work by Stevens, 2006, looking into the Tyrannosaurid dinosaurs. And his argument was that Albertosaurs, etc., their vision was not that binocular because, for one thing, their post-orbital width was narrow, and for another, their snout was quite tall. Whereas in T-Rex, I believe must be this one. This is eye socket, and the snout is lower compared to the eye socket, and also T-Rex, as you know, like Sue at Chicago, it's got really wide post-orbital skull region. So anyway, he was arguing that T-Rex had the best binocular vision amongst Tyrannosaurids. So I kind of followed his argument. Now, what you could see, though, tell that not only the binocular vision would provide a more accurate depth perception, it also allows an animal to see a same source of light using 2 sets of photoreceptors. Now you have 2 eyes and 2 retina layers to detect the single source of light. What that means is that is really good at detecting a slight, faint light in the dark condition. So you could use your binocular vision for not only predation, pursuit prey, predation, but also night vision, if you will. Now, notably, Photosaurs, which possessed larger orbits, had really poor binocular vision, as we saw. Yet they were supposed to be very fast-swimming mosasaurs, one of the most derived. So pursuit predation is one hypothesis, and then nocturnal lifestyle is the second. Now, what was paradoxical here was that based on the gut contents alone, we already knew that all the mosasaurs, the fish-shaped mosasaurs, were rather good pursuit predators because their gut contents showed everything was basically pelagic animals, be it sea turtles, which can swim fast, fish, ammonites, perhaps. They are all good swimmers, pelagic taxa. So, but then they really didn't. So, in other words, they really were not using the binocular vision or needing one to achieve what they needed to do. So, i.e., pursuit predation. But this nocturnal adaptation was something that never was, I guess, proposed or thought about concerning not only mosasaurs, I would argue, but also marine reptiles in general. So that's where we thought would go with this thing. So just coming back to this skeleton of Halosaurus or Ionitator, Sternbergii, with very poorly developed paddles, and same goes true with the tail fin, and rather skinny, long, slender body form, really doesn't seem hydrodynamically efficient, at least not more efficient than other larger mosasaurs based on this particular skeleton. And this is the type of the mosasaurs that Hokkaido specimen also belongs to, Halisaurine Mosasaurs. So it was really strange thing for us, at least, to think that they developed this extra binocular vision for predation, like a super pursuit predation. That really doesn't seem to work very well with their body plan. And also, if you remember, the sudden increase in the width of the head posterior to the eye sockets would create this extra turbulence and so on. So then we learned that also in this area of Hokkaido, the same time period and the same marine strata, we've known fossils of lanternfish. The living one is here, and also 10-armed cephalopods, like squid-like things, both of which are typically bioluminescent today. So rather than being a super swimming lizards, perhaps that's what they are going after. So by not only enlarging eyeballs, but also using both to focus on an object, single object, the optical biology of this Phosphorosaurus ponpetelegans, that should have been italicized, and other halosaurians may have facilitated their nocturnal lifestyle and allow them to hunt small and bioluminescent, perhaps prey items at night, likely employing ambushes because they perhaps were not that good a swimmer, not as an adept swimmer compared to other ones. And this perhaps worked very well for them, and probably that was key for them to just stay kind of primitive in terms of their postcranial anatomy, not really becoming fish-like, but yet conquering or dispersing so well across the globe alongside the larger, very fish-like mosasaurs. And they just, whenever you find, for example, Mosasaurus, you would find Halosaurus or Halosaurines. And this was what the Hokkaido new specimen seems to kind of, provided us to think and gave us opportunity to think about their biology from a rather unexpected angle. And that's what really a gist of today's talk. So I think with that, I would like to thank my co-authors, co-workers here, and of course, Mr. Shimoyama at Hobesu Museum, who was in charge of the preparation of that specimen for 2 years. Alan Lindo making those very well-made casts and also this reconstructed skull. And of course, special thanks to the museum here, Francois, Patty, and the Cooperating Society, the Tyrrell Museum, everybody else. And I am very happy to, I guess, be back here and given this opportunity to share some of my recent work concerning Mosasaurs. What a surprise. Thank you very much.